hear me? Is everyone that is presenting here today, or we have anyone missing? I think we have 5 papers, so can you raise your hands who is presenting? 2 of you. Okay. I think we have 5 papers, so let's wait for, I mean, no matter what, it will start in like 4 or 5 minutes.
So.我看那个刚底下有一个贝斯的一个数据库实验室，他送那个他们那个水杯，搞一个，等我去，你搞完就去，等我直接拿可能不合适。为啥？因为有人看，好多人。他看着有人了，你交流呗。我交，一直交。没事，你去了他会送。哪有人？他一般都是去了你就往你给完以后，你要愿意聊就跟你聊的。
3 out of 5. So welcome everyone. This is the beginning of the data mining and knowledge discovery session 3. If I remember correctly, we have 5 papers in this. It's not on. Is it better now? Okay. Welcome to Data Mining and Knowledge Discovery Session 3. We have 5 papers today. I think we have 3 of the presenters here. Hopefully the other 2 are going to appear as well. So we'll start with the first paper, TimeDRL, Disentangling Representation Learning for Multivariate Time Series. And we'll do the questions as always in the end. Thank you.
Okay. Good afternoon, everyone, and thank you for joining today's session. My name is Qin Chang, and I'm a PhD candidate at National Yangming Chiaodong University. Today, I'm excited to present our paper titled TimeDRL, Disentangled Representation Learning for Multivariate Time Series, which I've had the privilege to work on with my colleagues. Our presentation will explore how advancements in self-supervised learning can significantly improve the performance of various time series downstream tasks. In today's talk, I'll first introduce the backgrounds of time series data and some preliminaries for understanding both time series analysis and self-supervised learning. Following that, I will outline some current challenges with self-supervised learning in time series domain and the corresponding solution for each challenge. Finally, I'll walk through our proposed framework, TimeDRL step by step, and then show the experimental results at the end. So time series data is ubiquitous, found in wearable devices, the Internet of Things, electricity usage, and the emerging field of medical AI. In modern manufacturing factories, large amounts of production data are collected daily from sensors. Effectively using existing technology to analyze these time series data can significantly reduce a company's operational and maintenance cost. So the urgent need for time series data analysis has always existed. Traditionally, we need to have label data in order to achieve accurate time series analysis. But oftentimes it's very hard to collect label data with low cost. Recently, there has been a growing trend among researchers to first learn representations or embeddings from a large amount of unlabeled data using unsupervised representation learning or the so-called self-supervised learning. And then we'll fine-tune these models with a limited amount of labeled data for specific downstream tasks. We can see the huge success with large language models, which are also leveraging the power of representation learning. There are 2 types of pretext tags in self-supervised learning. These 2 pretext tags differ from number of samples involved. On the left one, On the left side is the self-prediction, and the self-prediction only involves one sample at a time. And the pretext text is formed with intra-sample prediction, which means that we use part of the sample to predict the other parts. And on the right side is the contrastive learning, which involves multiple data samples at a time, often only 2 data samples. And we want to predict the relationship among these samples. Predictive learning is very common in NLP, and the popular models are BERT and GPT. BERT use masked language modeling to predict the max tokens, and GPT use autoregressive objective to predict the next token. Compared to predictive learning, contrastive learning, on the other hand, is more common in computer vision. The renowned SimCLR is a very classic model utilizing contrastive learning. They first form the data samples with positive pairs and negative pairs using data augmentation. The positive pairs consist of 2 augmented images from the same image, and the negative pairs consist of 2 different augmented images from 2 different images. And the objective here is to make sure the positive pairs are close to each other, and the negative pairs are far from each other. Next, we want to discuss 2 types of embeddings in the time series domain: timestamp level embeddings and instance level embeddings. The first one on the top is the timestamp level embeddings. And these are a series of embeddings where each embedding represents a single timestamp. And this type of embeddings are effective for time series tasks like forecasting and anomaly detection. On the other hand, on the bottom side is the instance level embeddings, which represents entire time sequences. And this type of embeddings are suited for time series tasks like classification and clustering. We can observe that there is a huge similarity between NLP and time series when we're talking about the types of embeddings. The timestamp level embeddings is actually very similar to the token level embedding in NLP. For each timestamp level embedding, it corresponds to each timestamp. For each token level embedding, it's corresponding to each token. On the other hand, the instance level embeddings is very similar to the sentence level embedding in NLP. This is because the instance level embeddings encompasses the whole time sequence information, and the sentence embeddings encompasses the whole sentence information. Now we'll start to talk about a challenge in time series representation learning. And the first challenge is entangled representation learning. The reason why we mention the similarity between the time series domain and NLP is that it is actually well studied that when deriving sentence level embeddings by extracting them from token level embeddings using pooling methods, this approach often results in the so-called anisotropy problem. This means that the sentence embeddings are confined to a narrow cone region instead of uniformly distributed in an embedding space, thus limiting the expressiveness. And this phenomenon can also be observed in time series domain. If we derive instance level embeddings by extracting them from timestamp level embeddings using pooling methods, the resulting instance level embeddings would have poor performance in a downstream task. And this is because the deviation of timestamp level embeddings and instance level embeddings are entangled to each other. And the solution to this is pretty straightforward. We just need to derive timestamp level and instance level embeddings separately. And the second challenge of time series representation learning is the inductive bias introduced by data augmentation. With contrastive learning, we need to create 2 different views of the given sample to form positive pairs. However, using augmentation assumes that the augmented data must be aligned with each other. This strong assumption often violates the characteristics of time series data. For example, on the left, we can see that the sub-series consistency encourages the representation of a time series to be closer to its sample sub-series, but it is very vulnerable to level shift. On the right, we can see the temporal consistency enforces the local smoothness of representation by choosing adjacency segments as positive pairs, but it may introduce false positive pairs when anomalies occur. And the solution to this challenge is still very straightforward. We can just simply avoid use any augmentation methods at all. And to achieve this, we leverage the encoder's dropout layer's randomness to generate two different views from the same input data. And the third challenge of time series representation learning is sampling bias. When forcing negative pairs to be far from each other, we have a strong assumption that these two samples are fundamentally different. However, this assumption is problematic for time series data because time series data often exhibit periodicity. In such data, temporary distance points can be similar due to recurring patterns, meaning that negative pairs might still share significant similarities. So the solution to the sampling bias introduced by negative pairs is not very straightforward. We cannot simply not use negative pairs, because if we do this, we may suffer from the model collapse issue, which means that model would tend to memorize the input. Here we use the Siamese architecture, which is a symmetrical Siamese network with an additional predictor head to make sure that we won't have the model collapse issue. Here is our proposed framework, TimeDRL, which consists of the previous mentioned three solutions. To leverage the power of self-supervised learning, we first pre-train the encoder in the pre-training stage, and we leverage the pre-trained weight in the encoder and fine-tune the encoder for the downstream task in the fine-tuning stage. First, we will talk about how we derive the timestamp level embeddings and instance level embeddings in a disentangled manner. At the beginning, we need to pass the input time series sequence into instance normalization and patching. Patching here means that we will essentially divide the time series sequence into several patches. And the reason to do this is because we want to speed up the training speed, since we're using the transformer encoder, which is very time consuming. But before feeding the time series patches into our encoder, we will concatenate a COS token at the beginning. And this COS token is very similar to the COS token used in BERT. And this COS token's corresponding embedding would be the instance level embedding, ZI. And for each patch, we will also have the corresponding timestamp level embeddings, ZT. So by leveraging the extra COS token, we successfully employ the disentangled representation learning. And it means that we derive the timestamp level embeddings and instance level embeddings independently. Next, we want to talk about the self-prediction task in our framework. Since the predicted task is only relevant to timestamp level embeddings, we name the task as timestamp predictive task. After obtaining the timestamp level embeddings for each time series patches, we pass them into a timestamp predicted head to get the prediction of the original time series patches. So the predicted loss used here is actually the reconstruction error, which is calculated by mean square error. Last, we want to talk about the contrastive learning in our proposed framework. Since the contrastive learning is only relevant to instance level embeddings, we name the task as instance contrastive task. Remember that we need to have two different views in order to calculate the contrastive learning objective. But we also don't want to use the data augmentation to create two different views, since the inductive bias issue. Here, we simply pass the same data to the encoder twice. So here is the first pass, and we can see the second pass to the same encoder. And we leverage the encoder's dropout layer's randomness to create two different views. So here is the second solution, no augmentation at all. After obtaining two different views of instance level embeddings, we want to make sure that they are close to each other. Here we don't want to include the negative pairs since the sampling bias issue. So we use the Siamese architecture. For the asymmetrical Siamese network, we need to leverage additional prediction head. Here we name it as instance contrastive head. when calculating the contrastive loss, our objective is to align the output of the instance contrastive head from the first pass and the input of the instance contrastive head from the second pass. So it might be more clear if you can just see in the pictures here, and vice versa. Okay, and here we will employ the stop gradient for the input of the instance contrastive head because we don't want to have the model collapse issue. So this is the solution 3, Simsiamis. Since we pass the data twice, in the predicted task, we also need to calculate the loss for each view of the data. So for the first pass, we have LP1, and for the second pass, we have LP2. And finally, we use lambda to control the trade-off between the timestamp level loss and the instance level loss. So here are the final framework, which consists of the previous mentioned 3 solutions. This is for the pre-training stage, and our goal is to train a robust, express encoder to help with our downstream task. For the fine-tuning stage, we want to fine-tune our encoder to our downstream task. First, we will still pass the time series data into patching and transformer encoder to obtain the instance level embeddings and timestamp level embeddings as well. For instance level embeddings, we use classification to be our target downstream task. And for timestamp level embeddings, we use forecasting to be our downstream task. And for each different downstream task, we will have its corresponding linear head. And we only use a simple linear layer because we want to demonstrate the power of encoder with the pre-trained weight. Here are some descriptions for our experiment. For the forecasting task, which is used for testing timestamp level embeddings, we use 6 real-world datasets and 6 baselines. And for the classification task, which is used for testing instance level embeddings, we use 5 real-world datasets and 7 baselines. Before we jump into the experimental results, we want to talk about the general protocol to evaluate the performance of self-supervised learning. There are 2 common ways to evaluate. The first one is linear evaluation. It means that we first train the encoder with pretext text in the pre-training stage. And after obtaining the encoder's pre-training weight, we will fix the pre-trained weight so that it won't get updated in the upcoming fine-tuning stage. So as you can see, we use the light blue color to indicate that the transformer encoder's weight is frozen. And another important thing is that we only use a single linear layer to be our downstream head. And the reason of this is that we want to make sure the downstream head is simple enough so that we can actually evaluate the power of encoders. And the second evaluation protocol is semi-supervised learning, which I will elaborate later. The only thing we need to note here is that the only difference here is we don't fix the encoder's pre-trained weight. That being said, when in the fine-tuning stage, we will still propagate the gradients through the encoder and update the pre-training weight. Now we can take a look at the linear evaluation on multivariate time series forecasting test. And in this experiment, we want to evaluate the performance of timestamp level embeddings. And TimeDRL shows an average improvement of 58% in MSE compared to the SOTA method. Interestingly, when we look at the comparison between TimeDRL and SimTS, which is the best baseline, we can observe that the improvement is getting bigger and bigger when the prediction length in the future is also getting bigger. And this underscores TimeDRL's significant advancements in long-term forecasting accuracy. Although most time series data in the real world exists in a multivariate format, sometimes one may only care about a single important variable in a prediction. Therefore, we also evaluate univariate time series data, predicting only one variable at a time. Note that the input time series data here is still in a multivariate format. And in this table, TimeDRL shows an average improvement of 29% in MSE. Now we can take a look at the classification task. In this experiment, we aim to evaluate the performance of instance level embeddings. TimeDRL shows an average improvement of 1.5% in accuracy compared to the state-of-the-art methods. So to be honest, at first glimpse, TimeDRL might not seem very superior compared to other baselines. However, if we examine the results further, we can see that for datasets where baseline models already achieve around 90% accuracy or higher, TimeDRL can constantly maintain comparable results. And on the challenging finger movement dataset, which is on the first row, TimeDRL shows a significant 22% improvement in accuracy. And in semi-supervised learning evaluation, we aim to mimic real-world use cases. To simulate scenarios where labeled data is limited, we want to maximize the leverage of unlabeled data. If we look at the yellow highlighted circle here, it shows that the percentage of labeled data is only 50%. If in a supervised scenario, we only leverage this 50% of the data, including the corresponding labels. However, in a semi-supervised scenario, we first leverage all the unlabeled data to train the encoder with self-supervised learning, and then we use the 50% of the labeled data to fine-tune the encoder. Please note that when fine-tuning the encoder with labeled data, we do not fix the encoder's pre-training weight. As shown in the results, incorporating unlabeled data with TimeDRL boosts performance, especially as the proportion of available labeled data decreases. And the benefits of TimeDRL pre-training stage are evident even when 100% of labels are available. So even if we have all the labels we need, we can still benefit by our proposed pretext text. Okay, so in a sensitivity analysis, we aim to evaluate the impact of both pretext texts. The timestamp predicted test is designed to improve timestamp level embeddings, while the instance contrastive test is designed to improve instance level embeddings. However, the results shows that combining both pretext texts yields the best performance in both forecasting and classification tasks. Here we want to validate the idea that using extra data augmentation can introduce inductive bias, which could hinder the performance of downstream tasks. In the table, we can see that the application of any augmentation method leads to a decline in performance, with the most significant deterioration observed with rotation augmentation. While TS2 vector addressed the inductive bias issue, they still use masking and cropping augmentations. Our results shows these augmentations to be less harmful, but still detrimental to performance. Here we want to validate the idea that using pooling methods can introduce anisotropy problems, which could hinder the performance of the downstream task. Here are 4 different ways to derive the instance level embeddings. The first one is our proposed one, which uses the COS token. And the second one is to simply choose the last timestamp level embeddings as the instance level embeddings. And the third one is to apply global average pooling among all timestamp level embeddings. And the final method is to use the flatten operation instead of global average pooling. And we can see that using the COS token performs the best. Here we want to evaluate the choice of backbone encoder. And using the transformer encoder also along with our 2 pretext texts yields the best performance. Here we want to determine whether the stop gradient operation is necessary for preventing model collapse. And the results shows that using the stop gradient operations yield better outcomes, indicating that it is effectively prevents model collapse. Okay, so this is the illustration about the training time. As you can see, although our proposed model is slower compared to other baseline, we implement the patching to decrease the computational and memory demands quadratically. And we have made our code valuable and results are available on GitHub. So feel free to try our framework yourselves. And thank you for your attention here. And I appreciate your interest and will be happy to discuss any questions you have. Thank you.
Hello, we have time for only one question, maybe. Is there anyone from the audience? Something?
So in your evaluation, to me it was not entirely clear what you were comparing with, like what the baselines are. Are those like other representation learning frameworks?
Yes.
So you're only comparing to other representation frameworks, and then on all tasks like classification. So it's not that on classification you also compare to just pure classifiers, you know. Is that correct?
Yeah, but in the forecasting, we do also compare to some end-to-end framework.
Okay.
Yeah, but in classification, we only compare to other sales-supervisor events. Yeah.
Okay, it just might be interesting to see how it compares to, you know, some simple classification methods to see if you can.
Yeah, but we need to follow like the linear evaluation protocol because that's how we evaluate the sales-supervisor event.
Yeah, sure, but
Yeah.
if the baselines are not representation learning, say if they're just like a KNN classifier, then there's no weights, right? So no need to freeze anything.
Okay, thank you.
Let's thank the speaker again. Excellent. So we will move to the next presentation. Is boosting meaningful dependency mining with clustering